So I will present some work which has nothing to do with evolution, but with probability. So let me acknowledge maybe the two main contributors to this work. First, Félix Fautel-Roudier, who finished his PhD with Amaury and myself in December, and another very bright PhD student, Jean-Gilles Duchamp, who is now maître de conférence. Okay. So first, I would like to talk about not a model, but a general class of stochastic epidemiological model with an arbitrary number of compartments. And what I would like to convince you is that if you take those models, which are fairly general, then there is a very natural universal scaling limit that can be described in terms of the so-called McKendrick-Van Förster PDE. Okay? So the main motivation behind this work is that I think we're all convinced by now that the life cycle of the COVID-19 virus is fairly complicated with many compartments, and that all the textbook models that we knew, like the SIR or like SEIR, are probably not complex enough to kind of like represent like all the diversity in the symptoms that we can observe nowadays. Okay. So let me start with an individual-based model, okay, or a class of epidemiological models. So here the main idea is to distinguish between two types of individuals. So I want to partition my population into two types, first of all. So the first type is susceptible, and the second type is infected. And by infected, I probably mean something a bit broader than what is meant usually. I should say already infected. So infected means that you have been infected in the past. And what I would like to do now is to, every time I have an infected individual, I would like to characterize this individual by an age of infection. Okay? And the age of infection is the time which is elapsed since the infection's onset. So if your age is 2, this means that you have been infected 2 days ago. Okay? So now that I have those two types of individuals, I would like to complexify the situation a little bit. So every infected individual will be characterized by what I will call a life cycle process. Okay? So this will be represented by a stochastic process X, and X of A will be the class visited by the individual A units of time after infection. Okay? So if you take, for instance, a death trajectory, then you could imagine that the successive classes that will be visited by an individual will be exposed, pre-symptomatics, serious condition, hospitalized, and then death. Okay? And let me emphasize here that in this stochastic process, you don't have to make any Markovian assumptions. So for instance, you don't have to assume that you wait for an exponential amount of time before going from one compartment to another. Okay? So that's as general as it can be, so probably you have to assume that the state space is finite, but apart from this, this is fairly general. Yeah. Okay. Okay, so far I just described what happened at the individual level, so now I have to tell you how the epidemics will spread in the population. And the way we do that is that we characterize an individual by two coordinates. So the second coordinate here for individual X is the life cycle process that I described at the beginning. And the first coordinate is a random point measure. So it's an atomic measure that I will call the infection process. Okay? So you think of it as a random measure, as a random atomic measure. Each atom corresponds to a potential infection. So if you have an atom at 1, this means that 1 day after infection, you contact someone chosen randomly in the population, okay? Uniformly at random in the population, and then two things can happen, okay? Either the individuals you contact is already infected, in which case nothing happens, or otherwise, if the target individual is susceptible, then it becomes infected, okay? So this is very reminiscent of the standard assumption of the SIR model, except that now you can have a rather complicated infection measure. It doesn't have to be Poisson, for instance. And the number of compartments that you can visit can be arbitrarily large. Okay, so that can be as complex as you want. And of course, there could be a very non-trivial correlation between those two things. Okay, so you can recover like every standard models out of this class of models. So, for instance, if you want to get the SIR model, then the infection process will be a Poisson point process with a constant intensity measure, which is killed at an independent exponential random variable. Before the killing, you're infected, and after the killing, you're recovered. Okay? And you can already see from this standard model that, as it's written like at the bottom of the slide, there is a non-trivial correlation between, in general, between the infection process and the life cycle process. Since, for instance, if you die, of course, you're not infectious anymore. Okay? So I would like to just add like one more twist to the model. So for instance, if you want to model some control strategy or some change in behavior, I would like to have a certain contact rate. Okay? So this is exactly the same model as before, except that now there is a certain function t, a certain function of t valued in 0, 1. Okay? And what will happen is that if a contact occurs, this contact will be effective with probability 1 minus Ct, and you just ignore the contact with the remaining probability. Okay, so when C is equal to 1, you're just back to the previous model. And if C is equal to 0, then this means that you have a perfect control strategy, in which case the epidemics cannot spread anymore. Okay, so if you think of an intermediate situation where like you put like a lockdown into place, then you start with a C equal to 1 at the onset of the epidemics, and after reaching a certain threshold for the number of hospitalized, then C takes like an intermediate value between 0 and 1. Is the model more or less clear? Oh, yeah, okay. Okay, so let me mention that this model is not really new. I mean, there is already like a lot of work in this direction. So in particular, if you don't take saturation into effect, namely like every potential infection becomes effective, like at the onset of the epidemics, you don't feel the saturation in the population, or another way to put it, herd immunity, then this is directly related to a well-known object in probability, which are called like generalized or CMJ random branching processes. So if I take the terminology of the seminal work of Jaegers and Nerman, then you want to think of this infection measure as a reproduction measure. And the life cycle process is nothing else than the random characteristic associated to individual X. Okay, so I mean, this is kind of like a fairly like a standard model, and there are a lot of results which are known. So I guess like the difficulty of the previous models that I introduced is that you want to take saturation into effect now. And there is also a non-trivial contact rate, and as you will see, this can induce some kind of interesting effects. Okay, so before going into the mathematical details of our theorem, let me just introduce the results informally to start with. So the main quantity here will be the intensity measure of the infection measure, right? So P is the infection measure. So you take the expected value of this. So TU du is the average number of contacts that you make in between U and U plus du. Okay? And so in particular, if you want to recover what's called the basic reproduction number, then what you have to do is to integrate this intensity measure from 0 to plus infinity. So this gives you the average number of secondary contacts that you will make during the course of infection if you start with a single infected individual in your population. And so this is R0. And here what I want to assume for the rest of the talk is that R0 is less than infinity. Okay, but apart from this, that's about it, okay? And so here is what we want to prove. So the first quantity we will be interested in is not really the number of individuals in each compartment, but what I would like to describe as a first step is something which is not really observable, but okay, that's fine, which is the number or the rescale number of infected individuals with a certain age at time t, okay? And this will be denoted by NT-ADA, okay? So of course, this thing in general is a random quantity, but what we prove is that there is a certain law of large number. Yes?
Age is always infection age, correct?
Yes, yes, yes. There's no age structure in the population. I mean, this could be added actually, with no like further difficulties, but for the moment, age is like really like the age of infection. Yes, absolutely. Okay, so there is a law of large number. So this quantity is random, but it converges to a deterministic limit, and this deterministic limit, so this is the age structure at time t, is described in terms of the Mack-Henrich-Van Förster PDE. So if you're not used to this PDE, let me just describe it to you in a few words. So in this PDE, there is the PDE itself, the partial relation, the relation between the partial derivative, which is the first line here. And this is actually pretty boring. I mean, what this is telling you, so this is a transport equation, and this is just telling you that your age of infection is growing linearly with time, okay? So actually, like the partial differential equation itself does not carry too much information, okay? So now you have two boundary conditions because you have to assume that t and a are greater than 0. So first you have an initial age structure for the population. So here x is a fraction of individuals which are infected at time t is equal to 0. And you want to think of G of A, so this is a density, a probability density, as the initial age structure of your population, okay? So now here comes the interesting part, right? So if you look at the spatial boundary condition, NT of 0, so this is the number of individuals with age 0, so this is the number of newly infected individuals, okay? So NT of 0 is more or less the number of freshly infected individuals in your population. So how do you compute this quantity? Well, so first of all, you want to compute the number of contacts in your population. So here is how it works. So first of all, you count the number of individuals at time t with age A. So this is n of TA. And then you multiply this quantity by the average number of contacts for this age class, right? So you multiply this by the intensity measure. So this is tau of A. So this integral is really like the average number of contacts in your population. Okay, so that's the first step. But now you have to take into account that all those contacts are not necessarily effective. So first of all, you have to multiply this by the contact rate. So this is the C of t quantity here. And even if you actually contact someone in your population, you have to contact someone who is susceptible. So you have to multiply this quantity B of t by the fraction of susceptible in your population. Okay? So again, number of freshly infected individuals in your population, it's average number of contacts multiplied by the contact rate multiplied by the fraction of susceptible in the population. Okay? Okay, so that's the age structure, but as I told you earlier, this is something that you will not necessarily be able to actually measure in your population. So how do you recover the compartments? So it's actually quite easy. So what you do is that you average, okay, the probability. So if you want to have the number of individuals in a certain stage I, it's not a J here, sorry, it's I. So what you do is that you compute the probability that you are at I at age A, and you average the age over the age structure at time t, okay? So in other words, even if you start with a rather complicated model at the microscopic level with a lot of correlation between the infection measure and the life cycle process, at the end of the day, what remains at the limit is the age structure, which is just a one-dimensional partial differential equation. And once you have this one-dimensional partial differential equation, you just decorate it with the one-dimensional marginal of your life cycle process, okay? And what's kind of, I think, nice about it is that, again, all the correlation vanishes at the limit, and the only dependence that you have at the end is a dependence in this intensity measure. So you don't need to have any more details about the infection measure than this first moment, and the one-dimensional marginal of the life cycle process, and that's it. Okay? So there's a lot of simplification when you go to the limit. So here is a more formal statement. So again, you start with a certain fraction of infected individual and with a limiting age profile at time t is equal to 0. And what you do here is that you construct an empirical measure. So you sum over every individual that will be eventually infected in your population in the future. And so this is the empirical measure for the age and the type. Okay, so in this Dirac mass here, you have t minus sigma x, where sigma s is the infection time. So t minus sigma x is the age of infection of individual x. And the second coordinate is the status of the life cycle process at the age of infection for individual x. Okay? And so if you take this empirical measure, so it's a random quantity, you have a law of large number, you converge to some product measure, first the age structure and T of A that solve this differential equation, multiplied by this one-dimensional marginal for the life cycle process. Okay, and if you look at this theorem, I mean, informally this can be summarized in what I told you in the previous slides. Okay. Okay, so now how do you choose the parameters of the epidemics? So first of all, the first thing I would like to talk about is the initial condition, okay, the age structure at the reference time t is equal to 0. So here, just like a few words about it. So the kind of like natural way of choosing the initial condition is to assume that at time t is equal to 0, you started with a single infected individual, and assuming that you have a supercritical infection, then you have explosion of the number of infected. And what you would like to choose for the initial age structure is what you will get if you wait until the first time that the fraction of infected individual in your population reaches a certain level x, okay? And actually, I mean, this type of initial condition is directly related to what's called a renewal solution in the PDE literature. So let me just tell you in a few words what this means. So what you want to construct here is a solution of the Mack-Henrich-von Förster PDE, except that now at time t is equal to 0, you don't have any temporal initial condition because your solution is not constructed on R+, it's constructed on R. It's constructed on R, and the assumption that you would like to make is that first, the solution is non-trivial, it's not equal to 0 for every t, but when t is going to minus infinity, then this quantity is going to 0. Okay? And what this is telling you is that, well, the age structure that you see at time t is just the result of a single individual that started the infection at time t is equal to minus infinity, and then well, you had explosion of your solution. Okay? So this renewal solution is unique up to a translation, and so what has been proved, but in a rather restrictive setting, is that, again, if you look at the first time that your population reaches a certain fraction of infected individual, then the age structure that you see at the limit when the size of the population gets large is the solution of the renewal equation the first time it is equal to x. Okay? So since everything is defined up to a translation, this is uniquely defined. Okay. So maybe a few words about the literature. Of course, we're not the first one to look at these kind of models. There are many compartmental models in the literature, but more often than not, it is often defined in terms of a system of nonlinear ordinary differential equations. And I think this raises, I mean, two issues. From a conceptual point of view, you have to make some Markovianity assumption, okay? Because so you wait for an exponential amount of time before going from one compartment to another. And the second drawback is that, of course, if you're dealing with an epidemics with a large number of compartments, like in the COVID-19 situation, then, well, I mean, I don't know, like from a mathematical point of view, it's not very satisfactory because the dimension of your system of ODE will be equal to the number of compartments. And if you want to add some new compartments, then you will have to add more dimension to your system. So it's not necessarily very pleasant, okay? So our approach, between quotes, and I will explain why in a second, is that we propose to first model something which is not observable, namely the age structure of the population, and then to decorate the PDE with the life cycle process, and this is done just by a simple integration, okay? So at the beginning, I think, so now it has been a year and a half that we started working on this. We were quite happy about this, but of course, this has already been done before. And this is actually the first epidemiological model. I mean, this is the first one, really. Because if you look at the original paper of Kermack and McKendrick in 2007, they actually start by describing this microscopic age structure model, okay? And then, as an example, they show that the SIR model can be derived as a particular case. So I think from an historical point of view, it's kind of interesting because they started with these very general models and they proposed SIR as an example, which became like the kind of like textbook model. And then somehow, like, at least some of us forgot about this original way of representing an epidemics. And I think nowadays it's extremely relevant. So, okay. And also let me mention that there is a very rich literature on the convergence of age structure population. So before, so Etienne recently published like a couple of papers which are related to the type of model I just introduced, but there is some earlier work by Jäger, Sklebaner, Fournier, Méléard, Tran. I mean, a lot of people have worked on this type of model in the past. Okay, how am I with time? 10 minutes? 10 minutes, okay, so let me skip the inference then. Okay, so we fitted the curve like everybody else. Okay, I think we can skip this part. So let me maybe say a few words about contact tracing because this is probably, from a theoretical point of view, the main novelty of this work. So one motivation that we have for doing contact tracing is the estimation of what's called the generation time distribution. So tau, again, is the intensity measure of your infection measure. So this is the average number of individuals that you contact in a small window, a time window at time u. So if you divide it by if you divide it by R naught, the basic reproduction number, so this defines a probability density, okay? And so this is a very standard quantity in epidemiology. And so now what we would like to do is to get some kind of estimation of this quantity out of contact tracing data. So the general idea is to estimate this quantity from reported pairs of infection, namely individual A infected individual B. And so the way it works is at the time t, you take a freshly infected individual and you trace backward in time the chain of infection and you just report the successive ages of infection along the transmission chain. Okay, so this is what's represented on this diagram at time t. This guy was infected, and this is represented by this arrow here. And so now you go back to the age of infection of your infector, okay? So that's this time represented by this arrow, and so on and so forth, until you reach the reference time t is equal to 0 of your epidemics. Okay. Ah, j'ai encore plus de 10 minutes? Okay, so if I have nothing to say at the end, I can go back to part 2, I guess. Okay. Or more time for questions, exactly. Okay. So here is so just a few notations. So what I would like to model as a first step is what I will call the chronological chain. Okay, so the chronological chain is just a discrete time process, okay, where R of L for individual X is the time of infection of the L's ancestor, right? So ancestor 0 is yourself, ancestor 1 is your infector, ancestor 2 is the infector of your infector, and so on and so forth, okay? So I was infected at time t, then I go back to the age of infection of my infector, so that's R1, and then I keep on doing this until reaching the reference time, the reference time of my epidemics. Okay, so t is equal to 0 is not really the onset of the epidemics, but it's the time at which you start observing your epidemics. Okay, so at that time you have like already like a large number of infected individuals in your population. Okay, so this is exactly what I just told you. So R of 0 is just the time of infection of individual X, and if you take the difference so the increments of this chronological chain, then this is the age at which the L+1's ancestor infects the L's ancestor in your transmission chain. So for instance, here the age of infection is given by the time elapsed between this arrow and this arrow. Okay, so far so good? Yes. Okay, so now what I would like to consider is again an empirical measure. So what I would like to look at is this like horrible object, which I would call the historical process. So I take the empirical measure where I report the chronological chain associated to every individual present in my population. Okay. So again, we are not the first one to look at this. So let me go back to the branching process literature and to the seminal work of Jägers and Nerman. So what they do here is that they are considering a supercritical generalized branching process. Okay, they start from a large number of infected individuals, and they assume that the population at the reference time, t is equal to 0, my population has reached an equilibrium, namely that the initial age structure of my population is given by this exponential distribution. Okay, where alpha here is the so-called Malthusian parameter of the branching process, so the unique alpha such that this quantity is equal to 1. Okay? So now what they show is that if you make this assumption, you let the population grow to plus infinity at time t is equal to 0, so you're not at the onset of the epidemics again, then the chronological chain, assuming that you have been infected at time t, can be described in terms of a very simple mathematical object, namely a renewal process. So if I condition on the infection at time t, okay, so my process starts at t, and since I go backward in time, my renewal process makes negative jumps, okay? And the negative jumps here are chosen according to the density tau of x, which is the intensity measure of my infection process, multiplied by this exponential term, okay? So I start at t, and I find my the time of infection of my first ancestor by making a first increment with this density, and I keep on doing this until reaching an infector that has been infected before time t is equal to 0. So this corresponds to the ancestor of an ancestor infected before time t is equal to 0. Anything wrong, Amaury? Huh? It's frozen?
It's for remote participants. I'm trying to move the mouse so that they can see your pointer.
Ah, okay. I don't know. Okay, I can stop using the pointer maybe. Okay. Okay. Okay, so this is a mathematical statement of what I just told you. So if you take the historical process, okay, then what we prove again is a law of large number. So in this statement, there are two components. So first, you have some propagation of chaos. So first of all, if you sample two individuals chosen uniformly at random, then asymptotically, their chain of infection become completely independent. And the second part is what I just told you, namely that if you condition someone to be infected at time t, then the chain of infection is just given by a renewal process. Okay? And so the conclusion of this is that the successive infection time intervals, when you look at them backward in time, are given by exponential minus alpha x tau of x. And if you remember that what we are looking for is the generation time distribution, so tau x renormalized by its total mass, the basic reproduction number, you get that those successive infection time intervals are given by the generation time, but multiplied by an exponential bias, okay? And this is not so surprising, I mean, intuitively speaking, if you think about the fact that here, the epidemics is supercritical, so early infection will have a tendency to leave a very large progeny, and so if you sample at time t, you're more likely to sample an early infection than a late infection, okay? And this corresponds to this exponential bias. So the first take-home message is that if you want to have an estimation for the generation time distribution, you have to be a bit careful when you look at contact tracing data, because of this exponential bias. Okay, so you need to kind of debias the estimations that you get out of contact tracing data, and this has been discussed in a rather recent article by Britton and Tomba in 17, if you're interested. Okay, so back to the earlier model, where we want to now take into account first saturation effect and contact rates in our population, and maybe choose a more general initial condition than the one I just described before, namely this exponential distribution. And I think there is, a good motivation for doing this. So first of all, if you think about the recent stop-and-go strategies, particularly in Europe, then we are dealing with highly inhomogeneous contact rates. Okay, so I think at least in the current context, this has to be taken into account. And if you talk about herd immunities, then of course, making this branching approximation is not really valid, and it's kind of important to take the finite population effect into account. Okay, and I think, well, a good way to phrase it, and I don't think this question has been investigated from a practical point of view, but I think this is what interested me at the beginning, is, well, how is a chain of transmission distorted by a change in the contact rate or a high number of susceptibles? Of course, this contact rate is very difficult to measure in practice. It's very difficult to see whether a lockdown works or not. And the hope is that using this type of result, this will give you an easy way to kind of relate those contact rates, the change in the contact rate, to contact tracing data. Okay, so that's what we have in mind when we are talking about this. Okay, so this is what we recently put on the archive. So again, this is exactly the same object as before. This R is a chronological chain I was mentioning earlier, and H of n is the historical process associated to this. Okay. So as in the previous theorem, like in my first part, I assume that I start with a certain fraction of infected individual in my reference time t is equal to 0. And just to make things simple, this can be relaxed. You will see, like in a second, how this can be generalized. But I would like to assume that I have the same initial exponential H structure as in Jaegers and Nerman. Okay? So this is exactly the same model as before, so the branching model of Jaegers and Nerman. But now I assume that my population is finite and that I have a non-trivial contact rate. Okay? And so what we show is that if we look at this chronological chain, reporting the ages of infection backward in time, then the object that we get is very close, actually, to the Jaegers and Nerman renewal process. Okay, so, and this works like this. So you take your renewal process, same one as before, and now you kill it. Okay, so you go backward in time, and if after k steps, you're at site u, so a site now is really an infection time, so a site is really a time, right? So when you're at site u, you kill the process with a probability 1 minus C of, well, it's not C, sorry, it's not X, it's U. So it's 1 minus CU SU. Okay? So, which means that if the contact rate is very high and the number of susceptible is also very high, then this quantity is just equal to 0. So you're back to the renewal process of Jaegers and Nerman. Okay? So you take your renewal process and you kill it depending on which site you are visiting. Okay, and here S is again related, directly related to the McHenry-Van Förster PDE, namely it's the number of susceptible that is computed out of the analytical, out of this McHenry-Van Förster PDE that I described before. Sorry. Okay, so how is it related to the chronological path in the presence of a contact rate and saturation? Well, so what we can show is that the limiting process that you get at the end of the day is the kill process conditioned on survival. Okay, so you condition your kill renewal process on survival. And so from an intuitive point of view, I think this is kind of reasonable, because if you condition on survival, your renewal process will have a tendency to visit sites where this guy here is actually very small. Okay, this 1 minus Cx Sx is very small. Namely, you will have a tendency to favor infections at times where like infections were favorable, namely when C and S were very close to 1. Okay? So adding a contact rate and saturation effect into the picture have this tendency of biasing the renewal process of Jaegers and Nerman. Okay. So again, I started stating this result here. I started from a very special initial condition. You can actually generalize that, but it's just a bit more cumbersome to describe what is the result now. So again, what we do is that we take the same renewal process and we kill it exactly the same way. And because of the boundary condition of the McHenry-Van Förster PDE, it's not very difficult to show that if you construct the process here, yk, which is constructed from the killed renewal process, so here this is the renewal process itself, and here this is the indicator function that the process was not killed before time k, it's not very difficult to see that this guy is a martingale. Okay? It's a martingale, or another way to put it is that if you define this function of x on u, so here x, the x variable corresponds to my renewal process, u corresponds to the indicator function that I have not been killed at time k, then this is harmonic with respect to the generator associated to those two random variables. And out of this harmonic function, you can construct a Doob H transform. And what can be proved is that when you look at the historical process here, then you have convergence to a chronological path, which can be described in terms of this Doob H transform. But, so it's a bit more cumbersome, but it's just another way, or like a generalized way of conditioning your process on survival. Okay, so how is it useful? Well, I don't know, but I think what's fair to say is that infection times are, in general, kind of difficult to observe in practice. Okay, and what's observed is not really like the onset of the infection, okay, but the time between symptom onsets. And so, in general, if you look at the epidemiological literature, what's used in order like to kind of measure this generation time distribution is what's called the serial interval. So the time between symptom onset is used as a surrogate for the generation time. And as it was described in the same article that I mentioned before, this can induce a second source of significant observational bias. And so if you want to kind of remove this observational bias, what's kind of natural to ask is whether we can enrich the previous ancestral structure, so this chronological path, in order to take into account not only the ages of infection, but the life cycles of the infectors along the chain. Okay? And there's a very natural way to do this using palm measures. So let me skip this and just describe the results rapidly. So if you know what's a palm measure, here is how it works. So you take the chronological path that I just described before, which is in general defined by an age transform process. Then you look at the age of infection along the chain, which are defined by those AL random variable. And so what you do is that you take your chronological chain and you decorate it with the palm measure associated to this pair of random variable at the location of the atoms. Okay? Okay, so that's more or less it. And so just to summarize what I just told you, what we did is that we introduced or reintroduced a general epidemiological model with an arbitrary number of compartments. And this is quite flexible for inference. This is something that I didn't have time to show in the second part, but I think this is really tailored to make some nice inference procedures. So in the first part of my talk, what I showed you is that there is a very nice and universal macroscopic description of those epidemiological model. So first, you describe the age structure of your population using a McHenry-Van Förster PDE. okay? And once you have the age structure, you decorate it with compartments, okay? And the decoration is done in a very easy way. What you have to do is just a simple one-dimensional integration. And for contact tracing, it's exactly the same thing. You play exactly the same game. So first of all, the age structure along a transmission chain is defined as a renewal process, or more precisely, as the age transform of a certain renewal process. And once you have the age structure, you just decorate the transmission chain with palm measures, and you get like the full picture for your transmission chain. And with this, I think I'm done. So here are like two preprints. So that was the first project that we started a year and a half ago, dealing with the branching approximation of what I just told you. And I would say that this work has been a good collaborative work with all the members of the SMILE team at Collège de France, which is the group of Amaury, and was mainly directed by Félix Foutel-Rodier. So again, I really would like to highlight the contribution of Félix, who is really like an amazing student, and who presumably will be in Canada next year. And the second work has been put on the archive, I think, last Friday, and that's it. Okay, thank you.
Thank you very much, Emmanuel. I think we can take questions from the participants on the chat or from the room. Let's start with the room.
I guess you didn't really explain that, but I guess your tau of A is a given function of the law of X of A, right? Is it correct? Or?
No, it only depends on the infection measure. So it's like really the intensity measure associated to this infection process. So it doesn't depend on the life cycle at all. It's completely decoupled.
Can you?
Huh?
It's integrated over the life cycle.
Yes, but it's kind of defined, well, okay. So there is some dependence, but if you just give me the infection process, just this atomic measure.
What do you mean by infection process?
So the infection process is just the random point measure, which is giving you the potential contact with the rest of the population.
Yes, but you have to know whether that guy is infectious or not at that time.
Absolutely, no. So what I agree with you. So what you're saying is that there is a non-trivial correlation between the two, yeah. Right? So if you give me the life cycle, I have a lot of information about the infection measure. Yeah. That's true. But if you only give me the infection measure, regardless of the life cycle process, this completely determines what is tau. Okay. Yeah. So this is exactly. So this is the intensity measure associated to this point measure from a mathematical point of view. But regardless of the life cycle process, of course, there is a non-trivial correlation. Okay. So I think we agree.
But there are two things, right? There's the infection measure, which is highly correlated with the life cycle process.
Yes.
And there is the integrated infection measure, integrated over the life cycle.
Yeah, it's integrated over everything. Yes. Okay, that's another way to put it. Absolutely. Yes.
But how do you give yourself? You say it's highly correlated. How do you express this correlation or dependence?
So it depends on the model you're looking at, right? So it depends on the specification of the model. So if you give me the SIR, then I can translate the SIR model into this framework. But so it depends on the specification of the model. But I think like every mean field model, every one of them can be actually stated under this form. This cannot be more generalized than this. Because for instance, so something that maybe, yeah. Please, yeah.
Because if you think of a varying infectivity, which was already in the 27th paper of Clément McHenry.
Yeah.
Then this is infection age infectivity, which did not take values in a finite set. Okay. So I'm not sure that you can describe that exactly through.
Yes, you can. I mean, so the only assumptions that you have to make is that the contact matrix in the population is the identity. That when you have a contact in the population, the target individual is chosen uniformly at random. But nothing prevents that there is different infectivity values for the different individuals in your population. So here, like in this model, you could have two.
Age,
Yeah, exactly. You could have different age classes. The children could be like less infectious. Adults could be extremely infectious. And actually, you can put this in this framework.
But also infection depending on the infection age.
Yes, absolutely.
Sorry, infectivity depending on the infection.
Yeah, exactly.
Other question from the room?
I'm not sure I completely understand with this thing with the intensity, with the fact that if you follow one line of one person getting infections, you would expect that if I know that there is an infection at some point, so if the one is infecting someone at some point, is probably infectious, so I presume that just afterwards I would have an infection rate that is possibly a bit higher. So all these correlations in some sense kind of forgotten in the law of large limit description of the Mach-Dendrick, or is it
Yeah, I mean, it's what you are describing is just okay. So what you are describing now is I think is the correlation between time of infections, right? So if I infected someone at time 2, then probably that means that I'm very infectious, and so I'm more likely to infect someone at age 3. So there is a lot of correlation at the microscopic level, and I think what's kind of surprising is that at the limit, actually, this correlation becomes completely irrelevant. So now, of course, if you look at fluctuations around the law of large number, so if you look at central limit theorems, this will play a big role, but at first order, actually this correlation, so the correlation between times of infections that you described, or the correlation between the life cycle process and the infection measure, as discussed by Etienne, at the end of if you just look at the first order, it doesn't play any role at all. Okay.
Thank you.
Yeah.
Other questions? Yes. Maybe the last one because.
So looking at your at the last part that you presented about the contact tracing. So first you had this unconditioned process essentially, right? Not conditional survival, and there you could derive some explicit form how you would recover the infection process.
Mm-hmm.
Can you do the same in your final result? Do you get an explicit expression which you could estimate from data then the infectiousness curve? Or is it too complicated then? Because
you mean like? So can you repeat the question?
On the unconditioned process, you had this very nice, very explicit expression where you could decouple
the renewal.
Yeah,
so in the first part or in the second?
In the third part.
Okay, so the renewal process, yes,
Yeah, exactly.
yes.
And then you complicated the model
by adding some saturation effect and contact rates.
And do you recover in this model as well such a nice explicit expression for the, or is it too complicated?
I mean, it depends what you mean by nice, I guess. Like, yeah, it's more or less explicit, right? So you take the process and you condition it on doing something. Is it nice or not? It's a question of taste. But yeah, well, so it's as nice as it gets, I would say. Okay.
Do we have questions from remote participants? I'm looking at the chat. If you want to also ask questions on the chat, you may.